Okay, so good afternoon everyone. Good afternoon, Sir Akil. Today I would like to do the presentation about logistic regression for CDA mid-exam. So first, before we go in deeper, what is exactly logistic regression? So logistic regression is a statistical method to determine the relationship between independent variables and dependent variables. But in this case, the dependent variables need to be binary. So, for example, if I have two independent variables here, the first one is fish consumption, and the second one is weekly face injection. And the dependent variable is whether a person will have acne or not. And there can be two results. The first one is no acne. We symbolize it with 0, and the second one is someone who have acne. We symbolize it with 1. So in general, dependent binary variables can either be 0 or 1, yes or no, or success or failure. And then next we continue linear versus logistic regression. So for linear regression, as you can see in the graph here, it models numeric outcomes. So it is possible to have minus infinite and infinite values for the y. While in logistic regression, it estimates the probability of a certain event. So it has to be between 0 and 1. And in logistic regression, we use the sigmoid function in which the curve is shaped like an S. And the value, no matter what the value of x is, it's always maps y between 0 and 1. So for example, for logistic regression, it's predict whether a student passes an exam. It can either be yes, he passed, or no, he does not pass, based on hours reading. The hours reading here is the independent variables. And then next we continue to the sigmoid function. The sigmoid function is a mathematical function that maps any real number value, so it can be from minus infinite to infinite, into a value only between 0 and 1, as shown in the graph here. And a sigmoid function is actually like the inverse of the logit function. So if we derive from this the logit function, we can get P, which is the probability of y equals 1 given by this formula. And in general, if we want to make it like shorter, z, where z is equal to the linear regression. So yeah, this is for the sigmoid function. And then next we continue to the logit function. So logit function, logit T, is the log function of the odds of the probability of a certain event. So it is it's also known as the logarithm of the odds. So we have P here. We can say that P is the probability an event occur or success, and then 1 minus P is the probability an event does not occur or failure, and P over 1 minus P is the corresponding odds to the event. So this is the graph for the logit function. If you notice, then it's actually the x-axis in the logit function is the y-axis in the sigmoid, and the y-axis in logit is the x-axis in sigmoid function. And then next we continue to the regression coefficients, which is beta. So if you have positive beta, then it increases the likelihood or log odds of y equals 1. And if you have negative beta, it decreases the likelihood or log odds of y equals 1. So for example, if beta is equal to 1.45, then we can interpret that as the age increase, it also increases the odds of hypertension, in which this example will be used for other parameters as well. The next one, we are going to continue to odds ratio. This is the basic formula for odds ratio, so not specifically for regression. For OR, it's equal to odds in group A divided by odds in group B, where odds is probability of success divided with the probability of failure. For example, this is the probability of diabetes in which we consider diabetes as a success. So if we want to find the odds of diabetes for group A, which is the group with high sugar diet, then we get 0.6 divided by 0.4 equals to 1.5. And for group B with the low sugar diet is 0.2 divided by 0.8. So if we want to find the odds ratio, we can simply just divide the odds of group A and the odds of group B. We get equals to 6, which means group A is 6 times more likely to have diabetes compared to group B. And in logistic regression, we have a special formula, which is OR equal to E power beta. Actually, this is beta, where beta is the coefficient in the regression equation. If OR equals 1, then it means it has no effect. If OR is bigger than 1, then it increases the odds of the outcome. And if OR less than 1, it decreases the odds of the outcome. And then next is the example. Given the data as the following, it actually has 30 data, but I only put 4 as the representative. And determine the logistic regression equation and the odds ratio. So for assumption, we use female as 0, male as 1, not hypertension as 0, and hypertension as 1. Then we can do the coding in R where family equals binomial shows that we are going to use the logistic regression. And yeah, we immediately get the coefficients here in which the estimate is the value of the beta. Substituting the value of the beta to the logistic regression equation, we obtain the equation here. And then we can also determine the odds ratio by 2 ways. The first one is manual calculation using the basic odds ratio formula, and the second one is using the value of beta. So for using this one for gender, the one that we change is only female and male and assume they have the same age. So we substitute, since it's age 27 and female earlier, we assume as 0. So we have 0 here and then we get 0.479. And the odds is equal to 0.919, while for male age 27, we have 0.388 probability to have hypertension, and then the odds is 0.634. So the odds ratio is we divide the odds from the male group with the female group, and we obtain 0.69. And if you notice here, it's the same when we use beta gender is equal minus 0.37, which we obtain from the coefficients. And then the odds ratio for the gender is equal to 0.69 as well. For the age is exactly the same, and we also obtain the same result for the odds ratio. And then next, we are going for partial test. So partial test, each independent variable has an associated coefficient. Like earlier, age has its own coefficient and gender has its own coefficients. So the partial test measures the significance of individual variables, and it is usually done using the WALT test. So the WALT test formula for Zj is equal to beta j divided by standard error of beta j. And the p-value is 2 multiplied with probability of z bigger than actual value of zj, which is in a standard normal distribution. And from our example earlier, we have the estimate here is beta and standard error beta j, and the z value is actually zj, and probability, this column shows the p-value. And if p-value is less than alpha, then the parameter is statistically significant. If it is bigger than alpha, then the parameter is not statistically significant. The alpha value that we usually use is 0.01 and 0.05. So if you can see here, all the z value is larger than 0.05, and the variable age and gender does not significantly influence the occurrence of hypertension. And then next we move on to the overall test. The first one is manual. It's not entirely manual, and we also use R for this. So overall test measure like whether when independent variables are joined together, whether they can significantly affect the model or no compared to a model with no predictors, or we call it a null model. So it's null model versus full model. For overall test, the likelihood ratio test is used. And for g-square here is equal to -2 multiplied with log lig for null model and minus log lig full model. And the p-value is probability of chi-square greater than g-square. To find the log likelihood for both models, you can just simply use the log lig formula in R. And then for g-square, we compute with the log lig we have obtained, and we get g-square equals to 2.566. And then the probability of chi-square bigger than g-square using calculator is 0.2772. So the p-value is, when the p-value is less than alpha, the predictor significantly improves the model performance. Or when there is predictor, it can be more accurate. While if p-value is bigger than alpha, the predictors do not significantly improve the model performance. So from our case here, since the p-value is equal to 0.2772, which is bigger than 0.05, then we can conclude that the predictors do not significantly improve the model performance. And this is actually using the ANOVA. It directly gives the p-value of 0.2772 and the deviance of 2.566, which is the same with what we obtained here. And the next one is deviance. Deviance measures how well the model fits the data. There are two types of deviance, null deviance and residual deviance. Null deviance is deviance for intercept-only model, or when there is no predictor or independent variables, while residual deviance is full models with predictors or independent variables. When we have lower residual deviance, it means that the model fits the data better compared to the null model. So we also use the R. We're using summary model, and we obtain all of this information where null deviance is equal to 41.05 and residual deviance equal to 38.488. And then to interpret the deviance result, the delta deviance is actually quite small, only 2.566, meaning that the jump is not very high. So although the residual deviance value is smaller, and we can conclude that it fits the model, it fits the data better, but the difference is quite small with the null model. And then we calculate the p-value using R. We also obtain 0.2772 using the degree of freedom equals to 2, or the number of predictors. And so we can conclude that whether there is predictor or no, the predictors do not significantly affect the model fit. And then the next one is confusion matrix. Confusion matrix is a table that summarizes the performance of a classification model. It shows how many predictions were correct and incorrect. So for example, here I have the graph of sigmoid curve, and this shows the actual observation result, the actual result. And for a threshold of 0.5, when the value is below 0.5, it's null, while if the value is bigger than 0.5, we can consider it as a yes. So for example, point number 1, the actual is null, and when we take a line here, it's also fall in the null region. So we can say that it is true negative. because it results no and the prediction is also no. And then the second one, we have yes as an actual value and it falls at no region. So the actual is yes and then the predicted is no, which means the second is false negative or Fn. And then for the third one, this is a no, but it falls as in the yes region. So we can say that it is a false positive. And for the fourth one, it is a yes. Actual data shows it's yes, but it also falls in the yes region. So we can say that it is a true positive. And then for the model performance metrics, there are three. The first one is accuracy. It's the proportion of correct predictions out of all predictions. So this is the total of all predictions. And accuracy measures true positive and true negative. And then the second one, we have precision. It is also known as positive predictive value given by TP over TP plus FP. And the last one is recall, or also known as sensitivity, which is measured by TP divided by TP plus Fn. And then we have AUC ROC. So ROC is the receiver operating characteristic. It plots true positive rate or TPR versus false positive rate. So for the TPR, we can put it in the y-axis and FPR in the x-axis, where TPR is true positive divided by true positive plus false negative, and the FPR is equal to false positive divided by false positive plus true negative. And then for AUC, or area under the curve, so it's the one here, the value can be between 0.5 and 1. When AUC equals to 0.5, the model performance is equivalent to random guessing. When 0.5 less than AUC less than 1, the model outperforms random guessing, and when AUC equals to 1, it's the perfect model. So the closer the AUC to 1, it means the model is better. So if we have this one, this is the red line. If ROC is here and then the AUC is only this, equal to 0.5, then there is no difference between random guessing and using a model. While if the curve getting closer to this point, then we can say that the model is better. So